Neutrino Disappearance and NuFast.
Okay, so thanks for having me. I'm, as you said, just down the road, so you guys should all come out and visit sometimes. This is, two things. So one is this this paper I put out a couple of years ago, and then another one is two papers with Stephen Park, one of which was last year, and one of which is, I was actually thinking of posting it like right now at 2 o'clock while I was doing my talk, but I figured that was a little too adventurous. And the code for the earlier one is online. You could probably get it running before my talk is done. Actually, probably before I get to this part of the talk, you'll get it running. It's very simple. So just to start off, we're all, not all of us, but most of us, many of us are chasing BSM, like dogs chasing a car. Would we know what to do with it if we caught it? I think that's a question sometimes people think about, but often not. Right, BSM, sometimes you want to make it as simple as possible, one mass, one coupling, maybe a couple of detection channels. Sometimes it's very, baroque and complicated, it's got a lot of moving parts. But what happens when you do catch it? Okay, well, so obviously I'm talking about neutrino oscillation, so we discovered this, our nominal discovery date, we say is 1998. There's hints going back decades earlier. And actually it's a fairly rich sector. And not only is it fairly rich, the complicated is involved, the physics is involved and complicated and a lot of stuff going on, but also conveniently we can actually probe a huge fraction of that, with things we have in our hands, things we can build, things we can detect. So we have all this BSM in our hands that we can touch and move around, and we've made a lot of progress. So these are the 6 oscillation parameters and the progress over the last 25 years. So the first one is theta 2-3 measured by super K, since then it's not really gotten a heck of a lot better, to be honest. Nova briefly thought it might not be maximal. That's disfavoring there. They changed their minds actually like 6 months later. And we still don't know if this is, above 45 degrees or below 45 degrees or close to maximum, whatever. We'd like to know that. The next one is is delta m squared 3.1. This is the frequency associated with it. This tells you when and where those oscillations happen. Super K kind of not only measured that too. And actually now this has been measured by 7 different experiments, or 8, depending on how you count it. It's been measured separately with electron neutrinos by Daibe and Reno in 2012, which really narrowed it down. So we really know that. We don't know the sign of this yet. That's what this pink curve is. So we've got maybe 2 sigma, depending on how you count this one. So we don't really know this. We'd like to answer that one. In the other sector, we've got the solar parameters. We call this theta 1-2. This is measured by solar experiments going back actually in principle to Homestake, which actually had this answer. They just didn't know they had it, which is it's in South Dakota, but we claim this is a Brookhaven experiment because Ray Davis came from Brookhaven. And then eventually, Snow got it, and Canlan came in and confirmed it with reactor neutrinos. There's also frequency associated with it. Solar neutrinos are very bad at measuring this, but Canlan and a reactor experiment is very good. So we pretty much know what that is, but this has only been measured by 1 experiment. Although JUNO, which is not on this plot, came online about a month ago, and I'm hearing that they are probably going to already surpass Canlan's precision in the next couple of weeks. So stay tuned for that. I'm very excited about that. At this point in the history, we've measured a lot of things. This parameter, theta 1-3, people thought might be very, very small based on theoretical arguments, model building arguments, and they built Daibe and Reno, as well as Show and Double Show in France, to measure it, assuming it might be 1/10 of a degree or even smaller. It turns out that they got to 3 sigma in 3 days and 5 sigma in 50 days of data. And so they measured it actually very easily. So we know this one very, very well now. Now, once we were at this point, we've measured the other parameters. We know that they're all non-trivial, they're all non-zero, and we can now ask if CP is violated. And that's governed by the file parameter, which I'm calling delta here. And this, at this point, you can see up to there, we had no information, and then we started accumulating a little bit of information. Started disfavoring some regions of parameter space, and T to K is kind of disfavoring the 0 to pi region, although they kind of are walking back on that a little bit, and actually it's changed a little bit since I made this plot in the last couple of weeks. But we'd like to know where this is as well.
Sorry, so 0 value, is it?
So CP conserving is the top or the bottom, which is the same, or the middle. Right, so it's 0 to pi. So 0 is here, pi is here, 2 pi is up there. So the CP conserving values, yeah. So
it looks to be...
So 0 to pi are kind of getting disfavored at 2 sigma, depending on which paper has most recently come out. It could still be there, but we're not sure. It's probably in this region, but also another experiment is kind of disfavoring part of this region. It's a very complicated story, which I'm not really going to get into because...
Sorry, you mentioned there's a recent change. Just out of curiosity, what's the sign of the trend?
So the problem is there's Nova and T to K, which both have comparable sensitivity to this parameter, and they're measuring different things. So saying what is actually the global preferred value for this parameter is not a super well-defined thing, so that's why it looks this kind of like local maxima. It's like goes up and down and like all this screwy stuff.
But it looks like if it asks whether CP violation was observed, it's almost close, right? Because it's like 3C.
It's 2 sigma.
But
So
the white, okay.
So this is conserving right here.
Okay.
And that's at like, it's actually, well, last year it was at like 1.5 sigma.
Okay.
Yesterday's colloquium speaker would not find it convincing. if he learned this physics.
Okay, so I like to say there's, and this is, if I worded this correctly, then this is true. There's 4 known unknowns in particle physics. That's parameters that we know are there, we understand the physics of. They're well-defined questions, but we don't know the values of them, and they're all neutrinos. Right? So these atmospheric mass ordering, whether on sort of 3 is positive or negative, really what is going on in theta 2-3, if it's on the larger side or the smaller side, this complex phase that tells about CP violation of the absolute mass scale I didn't talk about, because oscillations can't probe that, cosmology and other things can probe this. We're going to focus for now on the complex phase, which is perhaps the most interesting of these. This is my outline. It's a whole bunch of stuff, right? Whatever. All right. Why is CP violating interesting? I think this shouldn't be a surprising thing. Once upon a time, it was shocking when CP violation was discovered. We now sort of take it for granted. But CP violation phenomenologically is usually proportional to this thing called the Jarlskog invariant, named after Cecilia Jarlskog. It depends on all the oscillation parameters and delta. This is the same thing for the CKM matrix and for the PM&S matrix for neutrinos. So there's 3 places that we know of in the standard model, well, in our model of particle physics, I should say, where there could be, they govern how much CP violation there is. In the strong interaction, we don't see EDMs, so CP seems to be conserved or nearly conserved. We don't understand this. If you normalize this to 1, this is smaller than 10 to the minus 11, so that's kind of surprising, I guess. People think maybe axion's related to this or whatever. Quark mass matrix definitely has CP violation. It is small, but non-zero, so it's 3 times 10 to the minus 4 times as big as it could have been. In the one-time mass matrix, we don't know. It's not maximal, but we're not nearly as constraining as in the quark sector.
It's not fair you didn't include number 1 in your list of particle physics known unknowns, right?
Which one? I mean, we've, yeah, okay, that's fair. We've constrained this very well. We have very strong probes, assuming it should be an order 1 number. We know it's smaller than 10 to the minus 11. But yeah, yeah, that's fair. I could have included it.
Entirely polemical, sorry.
Yeah, that's fine.
What's with the Jmax? With Jmax?
So the Jarlskog invariant is this thing here. It can't go up to 1. Okay,
Oh,
so you can show that you can't,
Because of the cosine.
yeah, there's cosines and cosines in there and all this stuff, right? And so you can show it's 1 over 6 square root of 3. You can draw a triangle also if you get yourself up to this. And it's about 0.1. So some people will just like quote values of the Jarlskog invariant, and I find it a little useless because I don't really know what that means, so I want to normalize it to something that has some meaning. Okay, good.
But just the value of the phase, that's also another measure, right? So.
Well, the phase is a parameterization dependent statement. I can actually write the matrix in a different way, and so I did this exercise in a paper. So like the CKM phase is typically written to be around 70 degrees or so, which seems big, right? It's close to 9 degrees maximal. But if I multiply the matrices in a different order, the corresponding phase is 2 degrees, which seems small. Physics is identical. So does the phase mean anything?
So, is there some conventional dependent state? When people say,
it's a
phase order 1, is there any
yeah, so it's
physical
a phase, it's a parameterization dependent statement, the phase delta. So that's why I specifically said the Jarlskog invariant, because this is parameterization independent. I've written it this way, but of course it's also the imaginary part of the product of 4 elements of the mixing matrix.
But people often say, CP is violated, like order 1 in your cover sector, because phase is order 1, but if one looks at your ratio, that looks pretty small. So
it is very small. The reason it's small is because, phenomenologically, the reason it's small is because, of course, the other mixings are small.
Right,
right?
yeah. So
right. So if you wanted to have big CP violation, you would need to have big mixing across the board, right? Because in order to have CP violation, the necessary requirements are three or more generations, and also you need to have mixing. If you have very small mixing, you can have CP violation, but of course it's going to be very small. In the neutrino sector, mixing angles are generally big, so you can have fairly big, in principle, CP violation. I know that I've also heard people say there's order 1 mixing in CKM, and I honestly don't really know what they're referring to. Order 1 of what? I would say it's 10 to the minus 4. And actually, in the neutrino sector, this is the kind of the status of that. So this is the total allowed region. Then as I add in experiments, I'm ruling out certain parts of it. This is kind of, you read this left to right. As you add in one more data set, you rule out a little bit more. So this is what you can totally have, going to the maximum Ural-Scoggin invariant. As you add in solar data from like snow or Camlin, that says that theta 1,2 is 34 degrees or so. You rule out a little bit there. But the most important thing in this whole parameter list is the fact that theta 1,3 is 8.5 degrees. That's what Diabet measured. And that rules out about 2/3 of the parameter space. Then T to K and NOVA, which as I said, they kind of are preferring this pi to 2 pi region, so it's ruling out a little bit, and it's kind of disfavoring here a little bit, so then we know a little bit more, right? So if we totally rule things out, if we totally rule out CP conservation, we might be, only down here. We're not there yet. I'm going to skip this. Okay, so the best way to measure CP violation is with appearance, which we'll talk more about that in a minute. But there's some other kind of non-standard ways that other people have pointed out that we're actually chatting about. And you can get some information from loops. So one way to get at CP violation, to see how neutrinos and antineutrinos are different, is the elastic scattering. So in elastic scattering, you have, this is where neutrinos scatter off electrons. And this cross-section is, it's largest for electron neutrinos, but there is a contribution from muon and tau neutrinos. That's about half as much, so it's not negligible. And because the cross-sections for muon and tau neutrinos are the same, the CP violation effect cancels. Okay? This is because the probability to go from the electron neutrinos in the sun to muon neutrinos plus the probability to go from electron neutrinos to tau neutrinos is the same as 1 minus the probability to go to electron neutrinos. So the CP violating effect cancels. However, something I said in there wasn't true, which is that the cross-sections for muon neutrinos and tau neutrinos are not the same, because in loops, the muon and the tau run in the loops, the masses are different, there's a small correction. And this has been trendy to look at recently in a couple of papers. This one by these people, anyway, the point is they did some study, and with Hyper-K and DUNE and a lot of years and no systematics, you can get a half a sigma worth of information. So there is information there in principle about CP violation. It's just super, super hard. Okay. And this is still basically an appearance measurement. This is going from electron neutrinos to muon neutrinos, is what they're getting at. You can also do this with atmospheric neutrinos. You're going below a GeV, there are some oscillation features there that are hard to see. Again, this is mu to nu e. Appearance is the other way for solar, the opposite way for solar neutrinos. But there's a little bit of information there going up to some values disfavored at the 3 or more sigma, 3.5 sigma level. This is pointed out in this paper from the Fermi lab in Brazil too. Okay, so I'm going to talk about the role of appearance and disappearance, which I've been saying, and I realize non-neutrino people probably don't think about these things as much as I do. And this has to do with the experiments that we have. In general, I'll just remind people disappearance is much easier than appearance, but we're trying to do better on appearance. And this is the alphabet soup of neutrino experiments. This is what some of my non-neutrino colleagues call it. They get very confused. We have all these acronyms. It's not just like the LHC, we just know the LHC, right? That's it. We've got all these things. Some of them are still running, some of them are not running. Actually, you just had to update this slide. JUNO now is taking data. So disappearance, we've got the lone baseline experiments, we've got reactor experiments, solar experiments are sort of disappearance, and then JUNO, DUNE, and Hyper-K will do disappearance as well as appearance. We've seen appearance clearly in T to K and NOVA. We've seen appearance clearly in OPERA, nu mu to nu tau. We've seen some appearance in atmospheric neutrinos, nu mu to nu tau. This is not that, it's below 5 sigma, it's about 3 to 4 sigma, although they have more data, they haven't analyzed. And then atmospheric neutrinos in general are mostly muon neutrinos, but significant, kind of 10 to 20% electron neutrinos. So that's kind of the whole picture. So just a reminder, the relationship between appearance and disappearance and CP and T and CPT. So for disappearance, let's take nu e disappearance. This is like what you see with reactor neutrinos. You then hit the CP operator on it, you get the antineutrino version. You get the T operator. The T operator obviously doesn't change anything. The CPT operator is some of both of those, and of course that can't change anything. And the fact that it doesn't, I'm assuming CPT invariance throughout this, doesn't change anything means that these things must be the same. Which means if these are the same, and since these are the same, then these two are the same. Okay, so you go around the triangle, you go back around the triangle, basically. What that means is that this probability is CP even, is an even eigenstate of the CP operator. Okay, this is pretty not surprising.
Is this all discussion assumes that neutrino Majorana, or it's not
It doesn't make a difference. So, I'm assuming that they're relativistic.
Mm-hmm.
When they're relativistic, Dirac and Majorana behave the same. Yes, that's a very good point. In the low energy regime for neutrino beta decay or the C nu B, these issues do play a role, and actually some of these stories do change.
But for nano,
the lowest energies we can see oscillations are like 1 or 2 MeV.
Mhm.
Neutrinos are lighter than an electron volt. The difference between Dirac and Majorana appears like m over e squared. So the difference between those is 1 in 10 to the 14. We can barely measure things at the percent level, so not gonna sweat that. Yeah, it's a very good point.
Sorry, I have what is definitely a stupid question.
Yeah, please.
Why doesn't T change anything?
T is going backwards,
Yeah,
so it just switches the thing on the right to the thing on the left.
but the probability can't change. Well,
I mean, the probability could change, but for disappearance, it doesn't change.
okay.
Yeah. So for appearance, it will change. Yeah. So this is for appearance. So nu mu to nu e. Let's start there. You do a CP. The antineutrinos. Then you hit the T operator. You flip the source in the end. And now you see that, of course, even though CPT says that these are the same, so the blue and the red boxes are the same, and those are in fact the same. But then, because these are not the same, what you find is that the appearance probabilities, they are not eigenstates of CP. They're not CP odd. They're both CP. They contain both CP even and CP odd parts. Okay. The kind of the conventional wisdom here is that appearance has information about CP violation and disappearance does not. But I will actually show that that's not entirely true. So how do we write the probability? There's a lot of different ways. You take the amplitude, you square it, but then that ends up being a mess. So what we do in practice is we do some trig identities and some unitarity things and we rewrite it, and it looks like this. So for disappearance, we got these 3 nice sine squared terms. Because these deltas here, these have L over 4E. L is like the thing that changes sign with the T operator. It goes L to minus L. So these are clearly even in T and therefore also even in CP. So this is a CP even expression, which is consistent with what I said a few minutes ago. The appearance probability has 3 terms that look similar. The coefficients are some messy things, but whatever. These are the same, but it also has this, what I call the triple sign term. So this is odd in L, therefore odd in T, and also odd in CP. So this has a CP even part, which is the first part, and a CP odd part. So if you do this in neutrino mode, and you do this again in antineutrino mode, this term down here changes sign. So you measure both of those, you do an asymmetry or whatever, and you get some information about CP violation, about the Roscoe invariant, which is the goal. Okay? So that's how you get, that's the conventional picture about how you get CP violation. So this is the conventionalism. This is what I've heard people, neutrino people and non-neutrino people tell me. Appearance is sensitive to CP violation, that's true. Disappearance has no CP violation sensitivity, that's false. I'll explain that in a second. You can see why, based on what I just said, people might think that. Then people, if they're willing to, give me some leeway on point 2, what they typically say is, okay, well, if it is true, it must be in the muon sector and not the electron sector. And the reason why they're saying that is because they think this is what the mixing matrix looks like. Disappearance, as you just saw, only depends on the norm squares of elements of this matrix. Well, the electron row, which is the first row, right, no delta there, and there's a delta there. We take the norm square of that, and that delta goes away. There's no delta information there. But the muon row, the second row, well, you're going to get some cosine deltas mixed in there with a bunch of garbage, right? So if there's any information, it's in the muon row. But really, that's not true either, because CP violation is physical. It can't be really fundamentally different between electron neutrinos and muon neutrinos. So what's going on? All right, here's the way that I think about it. So appearance is the best way to measure this. This is mostly an experimental statement, given what we can measure, but that it is a good way to do this. But disappearance can measure it, and you can do it with you can actually discover CP violation if we only had disappearance measurements. You have to measure 2 different flavors, though. In practice, that's electron neutrinos and muon neutrinos. And if you want to think about it, it works through unitarity. That's a little bit of a hand-wavy thing, because everything we do in neutrino physics, assuming unitarity, works through unitarity. But that's true there as well. So there's kind of a couple different ways, I think, to convince you that this is true, this statement. You can get information about CP violation from channels that are fundamentally CP conserving. One of them is parameter counting. There's 4 parameters in the PM&S matrix. We usually call these 3 angles and 1 phase. So if I measure 4 numbers, then presumably I can tell you if CP is violated or not. So disappearance experiments of one flavor, let's just say electron neutrino, for example, can measure 3 amplitudes. So there's 3 frequencies, delta squared 2.1, 3.1, and 3.2. Each of those has an amplitude for how much they oscillate at those frequencies. Okay, so for the electron row, CamLam measured one of them. JUNO's going to actually redo that measurement like any minute now. Diabay and Reno measured another one, actually measured an average of 2 of them. JUNO's going to separately measure all 3 eventually, not in their first paper. So the electron row is in very good shape, or it will be very soon. The muon row, we've got good measurements of one of them for Minos TDK node. They've got good disappearance measurements. The other one is the challenging one. We'll come back to that. So again, this is what the disappearance probability looks like. I've rewritten it a little bit, but there's some coefficient that you can just extract this from the data, and then you can map that onto the P-S matrix. So just for context, this is Diabay's result, so you see a dip. The depth of this dip here is one of those coefficients. This is what JUNO will measure. This is a sensitivity plot for them. This is the unoscillated spectrum. The big dip here is actually the same thing as what CamLam measure. That's what they're going to report soon. And that's one of the coefficients. And then the other ones is these little tiny wiggles here. If you do a Fourier transform of that, you get either this or this. So you can get either this peak up here or this peak down there. Those are the two other coefficients that they'll measure. So they'll measure all 3. Now, they'll measure 3 things, we'll measure 3 things in the electron neutrino row, but only 2 of them are independent, right? Because by unitarity, one of them is just the same as the other one. Okay. But let's say that we measure the electron neutrino row arbitrarily well, and that the RSM allowed to pretend that, and the muon neutrino row arbitrarily well. That gives 4 independent numbers, and that completely describes the matrix. So if there is CP violation, then this will tell me that. So the fact that the electron neutrino row looks different, that's just a parameterization choice, back to the point from earlier. This tells us about cosine delta, and if cosine delta is not plus or minus 1, then CP is violated. So that's what we're gonna do that.
Oh, Peter,
Yeah.
can you go back to the plot you had on that slide? You
Yeah.
had one with like, yes, the
This
normal inverted hierarchies.
Yeah.
So wait, is this something that what
JUNO.
JUNO will actually measure?
Yeah. Yeah.
Okay.
Yeah. So good. So I'm glossing over that because it's a different part of JUNO's physics goals, but what they're going to measure is either the red curve or the blue curve plus experimental uncertainty. So let's just ignore the experimental uncertainties for now, because for theorists, can you tell these 2 apart? Well, it looks very hard. If you do the Fourier transform, you either get a shoulder to the right or a shoulder to the left. Now, the height of these is proportional to several things, but one of them is cosine squared theta 1, 2 or sine squared theta 1, 2. From other measurements, we know which of those corresponds to delta m squared 3, 1 and delta m squared 3, 2. We also know that cosine squared theta 1, 2 is about twice as big as sine squared theta 1, 2. So the bigger one here is the cosine squared one, which I think is delta m squared 3, 1. I should be able to figure this out. Maybe I have that backwards. In any case, then if you know which one is bigger in terms of the delta m squareds, you then know the mass order. So if you know if it goes to the right or the left, then you know what the mass order is. So actually, in order to know the mass order, you don't have to know necessarily where you are on here, although it would be nice. You just have to know, does the shoulder go to the right or the left? Exactly the significance with which they can measure this is hotly debated, but we will know more probably very soon. Good. Okay, so I just gave this hand-wavy argument about counting parameters and said there's 4 degrees of freedom that we can measure with disappearance, and there's 4 degrees of freedom that we want to know, including CP violation, so therefore it must add up, which sounds good, but doesn't actually really prove anything. Right? Maybe there's some degeneracies there that we've missed. So let's suppose that we've measured 4 of these PM&S elements. So the ones in black are ones we've actually measured pretty well. The one in red is the tricky one, but we'll get some information about that soon. Can we get CP violation? You can. You can do this derivation, which is in the paper, and it's a bit messy, but you end up with the fact that the Yaroscope invariant is equal to this product of these things. So given even though you typically think of the Yaroscope invariant as an imaginary part of some complex number, you can actually take a bunch of real numbers without any phase information whatsoever, add them up in the right way, and get this. Now, obviously, as you'll see, this is just the absolute value of this. I can't tell if nature prefers neutrinos or antineutrinos in a given process. But I can tell if nature treats neutrinos and antineutrinos differently or the same at some significance. So how do we get to this u mu 2 squared? Right, this is the tricky one. So let's look at this disappearance probability, nu mu to nu mu. This is for DUNE-like parameters. You can do a similar thing for Hyper-K. And this is what the probability looks like as a function of energy. And actually, I've just zeroed in on one part. The actual probability starts over there at 1, and it goes way down to the 8th floor, or maybe the 7th floor, goes basically down to 0 and comes back up. Exactly how high up it goes depends on cosine delta by a little bit. You can see it's about a 1% effect here, right? And then it comes, and then it does it again there, but of course, as you go to lower energy, it's harder to measure. So what I did is I plugged into some software with some simulation details provided by DUNE, and showed what the event rates will look like with 6.5 years just in nu mode. They'll also do anti-neutrino mode, but the statistics are a little bit worse. You can split this into 2 regions, just kind of by eye, and you'll find that in the different regions it varies by about 100 events per category. Okay, there's also some shape information too. So you can see here there is certainly information. This really is there. It's not a lot of information, so you can maybe guess the significances, but there's information there. I'm going to just, this is where you try to guess how big that effect is when you first do it the wrong way, and then we're going to do it the right way, actually. So how big is that effect, right? I said it's 1%, it looks like it's 1%. Can we understand that? So it comes from this solar interference term. Okay? This is where you get that higher order correction that allows you to get to this final term needed for CP violation. But you need to include the matter effect. The matter effect is pretty important for DUNE. So the delta m squared 2, 1 here is normally, it is 30 times smaller than the other delta m squared. But in the presence of matter, it actually gets bigger. It's about 3 times bigger. So this provides a decent sized enhancement, especially because it's squared.
What's S?
S is this modification for the presence of matter. So A is the size of matter. So it's proportional to the density of the Earth and the energy of the neutrinos. So this is some approximate correction term we derived that is not exact, but it's actually pretty good. So the relevant frequencies as far as when neutrinos oscillate in matter happens at a different point than when they happen in vacuum. I'm going to talk more about that later. So this frequency is actually 3 times higher in matter, which is kind of a lot. Although it's a suppressed frequency to begin with. So yeah, mixing angle is also modified actually by quite a bit. It also changes sign. So the sign of the effect in vacuum is different than in matter, which actually has a curious effect for Hyper-K. In any case, yeah, in the interest of time, I'm going to just skip through it, and you can show by adding in all the corrections, which I'm not going to go through, but it's about a 1% effect. So you take cosine delta, and it increases and decreases by about 1% depending on the value of delta. So there is some signal there. You can actually show how this comes right out of the probabilities. All right, so now I'm going to do, that was the second part, kind of doing this analytic derivation of this. Now I'm going to do this numerically, which is for some people the most convincing, is you just plug it into some chi-squared fitter. You put in priors based on other data, but of course I made sure to only use data from disappearance experiments. So diab tells us what theta 1,3 is, Kemelin tells us the solar parameters, and then I use JUNO, their projective sensitivities, and I'll use DUNE only for disappearance channel. I also look at Hyper-K, and it's pretty similar. So these are the numerical results. So these are for different true values of cosine delta. These are for different test values of cosine delta, assuming true values of either +1 or -1. So let's say cosine delta is really +1. Then with DUNE data plus what we currently know, so without JUNO, we're on this dotted line there. So we can rule out some values if we ran DUNE for its full run at like over 1 sigma, so like not very much. But with JUNO, we can rule out JUNO plus DUNE together. We can rule out some values of delta at over 3 sigma, which I think is pretty good. If JUNO ran forever, we could get to the solid curve. We could get to like 4 sigma. If DUNE ran for longer, we could also do better. Then I made the McDonald's plots. These are the standard things we do in neutrino physics, where we would say, at what level can you rule out CP conservation? So 0, pi, 2 pi, CP conservation. So it's basically this plot, but just marginalized in a different way. So the orange curve is the information you get from appearance. Obviously, that dominates. That's the best way to do it. The green curve is what you get from disappearance, again, under different assumptions. So it's 1.5 sigma, because we're trying to rule out things from ±1. So you don't get as far. And the combined is a little bit better. Okay, so it's not a lot of information. You can do the same thing for Hyper-K. It looks pretty much the same. And if you run for longer, you really need both, right? The information is really coming from both DUNE-like experiments and JUNO-like experiments. That's what this shows. Okay, so before I go on to the next thing, I just want to say that the real benefit to this is that disappearance has different systematics than appearance. Right? It's cleaner. It's also just a valuable cross-check. The cross-sections are different, so there's a lot of advantages to doing this, to factorizing an analysis into both. And I'm hoping that the experiments, and I think they're coming around, we'll do an analysis, both a full analysis, but also set it up, split it up into appearance and disappearance to confirm that we know what we're doing.
What's a star?
That's just some benchmark for how long that's just like the benchmark point. So all the JUNO sensitivity papers are with 6 years, and the DUNE sensitivities change all the time. But at the time when I did it, their benchmark number was 13 years. Okay, so that's the first half of my talk, which I'm pretty much on time. So I'm going to talk about something different, but related, which is this paper with Stephen from last year, and then the follow-up paper that's coming out whenever I get around to posting it to the archive, which is a fast code for long based on neutrino oscillation probabilities in matter. Code is online if you feel like playing with code. It's actually a very short piece of code and hopefully compiles. So the problem is, I mean, it's what we were just doing in some sense. Given the oscillation parameters in the presence of matter, you want to compute the oscillation probabilities. Okay, how do you do that? Right? It seems very easy. In principle, it is easy, but there are choices to be made. So what we're doing is we're solving the Schrodinger equation. Okay, so in long baseline experiments like DUNE and T to K and T to hyper K and so on, this, even though as you go into the crust and out, the density changes a little bit. People have shown it doesn't matter too much. So you can basically take this to be constant, so you just exponentiate this and then square it. Right? So that seems very easy. What is an exponential of a matrix mean? It means you have to compute the eigenvalues and the eigenvectors, but this is a straightforward thing. You go to your computer, say, please do this for me, and it does it, and it's right, and it's happy, and it's fine. It's actually pretty slow, but so there's room for improvement. You can also start with the oscillation probabilities as I showed them earlier, where I've multiplied them out, I've done my trig and unitary identities, I've got the sine squareds of delta m squareds out there, and then modify them for the terms that are relevant in matter. And people have been doing this in various ways over the years, and that's kind of the approach that we're going to be taking for the first part of this. Now, is this important? This seems like, again, we're talking about a 3x3 matrix, right? How hard could this be? This is an article from 2018 from Fermilab for a NOVA analysis. NOVA is the current long baseline experiment in the US. And they were doing one of their oscillation analysis, and it took them 35 million core hours to do it. So that's kind of a lot. And actually, the computer science division at Fermilab looked at this and said, why is this taking so long? And it turns out that the majority of the time spent was computing neutrino oscillation probabilities. And they reached out to Stephen and I and said, can we do better? Why does it take so long? Right? It seems a little strange. So the basic reason is Wilks' theorem is often wrong. Right? So anybody who does any statistical tests, probably doing Wilks' theorem, you compute a chi-squared, you assume that for some number of degrees of freedom, you can immediately convert that into a significance. Right? This is basically, you go to that little lookup table and you say that 2 degrees of freedom, you need for 95%, you need a chi-squared of whatever number that is. But that's often wrong in reality. And actually, neutrino experiments have a long history of Wilks' theorem being super duper wrong. So instead, what we do is what's called Feldman-Cousins, which is actually a bit of a misnomer. Ask me about that later. But it's basically just Monte Carloing the experiment at every point in parameter space. So let's say there's some real contours from NOVA. And let's say you wanted to know how to make these contours. So at every point in these parameter spaces, theta 2, 3, delta m squared 3, 2, you simulate your entire experiment. You simulate it many times, and you vary the other parameters many times. How many is many? Well, if you want to do a 2 sigma, this is actually 3 sigma, let's say you want to do 2 sigma, you have to have many more simulations than 1 over the probability. 1 over the probability is 20 for 2 sigma, so let's say you want at least 25 events, so you have fluctuations smaller than 1 in 5 sigma for this, so that's 10,000, I think, simulations. And then you want to do this for each point here, which let's say you want a 100 by 100 grid, and you want to vary other oscillation parameters. You can check, you quickly get into the billions to trillions. Right? So now we're talking about real computational time. And that's just for 2 sigma. 3 sigma is another order of magnitude. And really, the next generation experiments, of course, are aiming to be 5 sigma. That's another couple of orders of magnitude. Plus, they have better energy resolution, so you're going to have more grid points there. And according to the DUNE physics coordinator, at least one of them, they say that just for the sensitivities, which they're doing right now, they require computing the probabilities that I'm quoting a zillion times. So it's worth thinking about this. I'll skip that. So how to achieve speed? So this is shifting gears a little bit and something that I didn't normally think of, and it's kind of very stupid things. But how to make your code fast, right? And this is for very simple physics problems, which is just compute some straightforward thing a zillion times, right? So avoid costly operations. So sine, cosine, and their inverse functions, they're the slowest things. They're very slow. Square roots are also pretty slow. So you want to avoid those. If you can do any tricks to limit that, that's good. Division is slower than multiplication, right? This is very stupid. 0.2 is faster than x over 5, right? That seems stupid, but it's true. You can check that. Avoid complex numbers, right? Complex addition is 2 additions. Complex multiplication is 4 multiplications. So let's try to do everything in real parameters as much as possible and stick on the complex parts at the very end, if needed. And then if there's any repeated computations, right, don't do the same thing a bunch of times. Don't divide by the same thing a bunch of times. Divide by it once and then multiply. So how to write the probability? If you start with the amplitude and then you square it, you can show that that's actually one more trig function than multiplying it out. So we do that. So we write the disappearance probability like this. This is what we've seen before. These V's, this is like the PMNS matrix, but now it's the in matter part. So this is what we're going to have to compute. And instead of the delta m squares, I call these delta lambdas. So these are the eigenvalues. So you have to compute the eigenvalues and the eigenvectors, but then you just stick them into this formula and you get the probability. For appearance, it's a little bit more complicated. Remember, we had this thing with like 4 times the real part of some complex thing. But it turns out you can rewrite that to just be the norm squareds of elements of the matrix that diagonalizes this. So you can actually get rid of all the complex arithmetic in here. And this term is the imaginary part, but there's something called the Naumov-Harrison-Scott identity that relates the imaginary part of this in matter to the imaginary part of this in vacuum. So you can actually get rid of all the complex arithmetic. And what we have now is we have the probabilities as a function of the eigenvalues, these lambdas, and then the norm squareds of the elements of the eigenvectors. Okay? So it sounds like we haven't really made a lot of progress, but we have, I promise, and this is something that Josh wanted to know about, is so we start with the eigenvalues, and okay, I just said this, you can compute the norm squares of the elements of the eigenvectors from this thing called the eigenvector-eigenvalue identity, which we sort of accidentally stumbled across doing these work for this kind of physics, and then we published it with the mathematician Terence Tao. And what it is it says that the norm square of the elements, this, is equal to this, this ratio of products of differences. So the denominator is the product of all the differences of the relevant eigenvalues. And the numerator is the same thing, but the size are the submatrix eigenvalues. That's the eigenvalue of the same matrix when you delete 1 row and 1 column. Now remember, start with a 3 by 3 matrix, you do delete 1 row, 1 column, 2 by 2 matrix, that's just a square root. It's just quite right. That's very easy. And actually, you don't even have to compute the square root because when you multiply it out, the square root goes away. So you can see now that if I calculate the eigenvalues, if I get those from somewhere, I'd have to calculate these other little submatrix eigenvalues, which are super easy. I then get the norm squares of the elements of the PMNS matrix, which by these other complex analysis tricks that I showed previously gives you the full probabilities, including the CP violating parts. I think that's pretty cool. And this is actually where like all the speed benefits come from, is basically this.
Is Terence Tao that famous mathematician at UCLA?
Yeah.
So, wow.
Yeah. Yeah. There's a whole story.
You
there.
didn't know he works on neutrino physics?
He works on neutrino physics.
Great.
No, not really. Just this. So how do you get the eigenvalues? You always think eigenvalues are easier than eigenvectors, but I just showed you that if you get the eigenvalues, then you have the all the eigenvector information you actually need for effectively diagonalizing this matrix. And actually, the eigenvalues are the pain. They're a huge pain. There's no real, there's no easy way to do it. This is the exact expression is some long thing which I'm not even going to write down. But it depends on this quantity here, which is cosine 1/3 inverse cosine of something, right? Inverse trig functions, right? They're terrible. They're not fun for anybody. And there's other square roots and other nonsense out there. These ABCs are the sum of the eigenvalues, the sum of the product of the eigenvalues, and the triple product of the eigenvalues. These are easy. We can write these down. These are just the vacuum parameters. So these follow in a pretty straightforward fashion. You then plug this into here or some other stuff. But obviously, we would like to avoid this if possible. This does work, and you get these eigenvalues from this. You then go all the way up the chain. You get the probabilities, and you're done. Can we do better? Can we be more intelligent? Can we use more physics information? The answer is yes. We can approximate one eigenvalue. We're going to approximate the best one, the easiest one, and then bootstrap that into the other 2 eigenvalues, and then run it all the way through the chain. So the way we do that is we take lambda 3. So you can convince yourself that lambda 3 has the fewest features. It also is never parametrically small, so you don't run into any small number problems. And it's extremely well approximated by basically a 2-flavor problem with a square root. We did a lot of work to figure out that this is the best way to do that. And then you can get the other 2 eigenvalues by just requiring that you solve 2 out of 3 of these equations. Obviously, if you solved all 3, you'd get back to the exact ones. This sounds like a lot of work to do something that maybe isn't going to make much of a difference. I'll show you what this means in a minute. Now, maybe this approximation is good, maybe it's bad. If you want it to be better, you can actually iteratively improve it by just using Newton-Raphson methods, right? Because we know it has to satisfy the characteristic equation. It has to be an eigenvalue of the Hamiltonian. And we can take the derivative of this analytically easily. So you can just iteratively do this. And the precision without doing this is 10 to the minus 5, and you get 5 or more orders of magnitude for each additional step. So like in code, this is just one line of code, and you can do this as many times as you want. So is this approximation okay? Yeah. So these are the error and the probabilities with this approximation if you don't do it in solid. So this is energies. This is for like DUNE, like configuration, and you see it's like 10 to the minus 4 or better. If you do this correction that one time, then in Raphson correction, you get like, I don't know, 5, 6 orders of magnitude. So it's good. These experiments cannot measure anything this precise. How fast is this algorithm compared to other things in the literature? Right? It's called NuFast, so it must be fast, right? I mean, the branding, right? The name is half the battle. Is it actually fast? The answer is well, yes. This is the time it takes to compute one probability. Remember, we're doing this billions to trillions of times. We did the vacuum probabilities, which you can kind of think is the fastest conceivably you could possibly do this. And our algorithm is just a little bit slower than that. As you added more Newton-Raphson corrections, it adds very little time. If you do the exact cubic equation, it's again a little bit slower. This is by this guy, James Page. He wrote a paper around the same time. It's slower. The different DOS are for different compiler and computer languages. Globes is a very popular tool. It does a lot more than this, so it's not a totally fair comparison. But the part that just computes the oscillation probability is quite a bit slower. So it is fast. How to use it is very easy. You just call this function, you just plug in your oscillation parameters, and it spits out the answer. So that's it. The code is there. It's also used in what's called Mach 3, which is the main software analysis, which we just got it in the last year or so for all the neutrino oscillation experiments. TDK, NOVA, DUNE.
What's vacuum?
Sorry?
Vacuum. You had one point that was called vacuum.
Yeah, so this is, if you write the oscillation probabilities just for vacuum, you don't use any of the matter effects. This is basically like the simplest possible thing. And what we wanted to show was like, that's as fast as you could conceivably be. Obviously, including all these matter effects, you have to actually diagonalize a matrix. It's going to be slower than that. We wanted to say, are we close to that? And we are close to that. And is this as fast as you could possibly be? Obviously, no. I'm sure that someone can do something better. But how much better? How much room for improvement is there? And the answer is not very much. Right? I mean, somebody can get 10%, 20%, shave off that. But I think based on standard things that are commonly used, we brought this down by a factor of 4 or 5 already. And compared to what was used by the experiment, it's a factor of 20 faster. And they've already benchmarked this one using this in analysis today.
Peter,
Yeah.
in the beginning you were showing like the e to the h t or hl or
Mhm.
something, right? You were
Yeah.
approximating h as relative as constant over the.
Yeah.
Is that is that assumption in this
Yeah,
code?
yeah. So for this, we're assuming that the density profile is constant through the entire route.
Right. So what are the corrections to that for the delta p over p that you showed?
Yeah.
Is that
So good. So there's two ways I'm going to answer that, which might not be the ways that you want. The first is people have checked the impact of that on the probabilities and how that affects the experiments. And for long baseline experiments like DUNE and Hyper-K and things like that, the effect is far below what they can measure. So yes, you are, like for DUNE, they start at the surface, the detector is, well, it's underground, but it's not that underground. The neutrinos actually go quite a bit into the crust. In fact, they go closer, they go almost all the way through the crust before they come out. Obviously, the density increases as you go down. So people have very precisely solved things along that and compared it to assuming it's the average density and found that the difference is at a very small level. I don't remember what the numbers are, but it's very small.
Okay.
The other thing I can say is, what if the density is varying a lot, then this doesn't work, but that's the next part of the talk for atmospheric neutrinos going through the center here. Yeah. Good. Yeah, so this is being used by experiments, and they seem to be excited about it. And what they keep asking for is things to the Earth. So this is something we've been working on the last year, and it's almost done. So exactly to this point, you said that perfectly. As you go through the Earth, you've got the core, you've got the inner core, the outer core, the inner mantle, the outer mantle, all these layers. These densities change a lot. You can't average things across a sharp boundary. Right? Basically, what happens at the boundary to the neutrino state, if you think of it as like a vector, it enters into a new, it'll propagate in a new basis when you go into that next layer. And that has to be accounted for in a more complicated way. So that's what Steve and I have been working on recently, and we're done. People keep asking for this. Yeah, this is what I just said. Good. So we can reuse some things. We can use some of the eigenvalue and eigenvector stuff that we did before, so that kind of core linear algebra and complex analysis stuff. But there's a couple of key changes. Actually, there's quite a few key changes. The problem is more complicated. We're asking kind of a different question. So one thing we do is we pull out some of the rotations and we solve a different Hamiltonian in a different basis. And we stick those rotations on in the end. And the reason is because this rotation commutes with the matter potential. So you can propagate all the way through the Earth in a different basis and ignore this completely. And this actually pulls out all of the complex information. Remember I said I want to avoid that complex arithmetic because multiplications are very expensive. You can split it up. This also means that if I want to change theta, if I do a computation for a bunch of energies and a bunch of angles through the Earth, and then I want to change theta 2, 3, I actually don't have to recompute very many things. In fact, I don't have to recompute almost anything. I just have to do a couple of small matrix multiplications on the outer ends of this. So the code will actually save all of those computations in the middle if you're just changing certain parameters. So I worked very hard to get that to work, but it works. We can consider a bunch of different models of the Earth. So if you want to vary the Earth, if you want to consider an Earth with a lot of detail or just a very coarse-grained Earth that'll be computationally faster, you can do that. And we do a bunch of other things to make things faster. So this is what the Earth looks like as a function of radius. There's kind of, as I said, 4 main parts. And there's different ways of handling this in the literature, and we also define some of our own different ways to handle this. We split up a trajectory. So let's assume we've got a detector here at some number of kilometers beneath the surface, and assume that the neutrinos are produced in the atmosphere at some height above the Earth's surface. So the first thing I do is I go from the production point to the Earth's surface, which is in vacuum, which is super easy and can be redone very rapidly. I then do a very short trajectory, which is from the surface to the depth, that is the detector depth on the other side. I then go from that distance to the deepest point in the Earth along the trajectory, and then I go out. Why do I split it up into these 3 parts in the middle? Well, because the blue and the orange are the same. Assuming that the Earth is spherically symmetric, the orange and the blue amplitudes are just the transpose of each other. So when I compute one of them, I just get the other one for free. And if you have many layers in the Earth, this can save a lot of time. As I said before, I'm going to pull out this 2, 3 rotations. I'm going to work in a modified basis, which I call the tilde basis, which is fine. This makes things a lot simpler. I'm not going to go into the details of this. The vacuum propagation of the atmosphere, again, can be done very quickly, and this is something experimentalists really like to do, is to integrate over production height. So where neutrinos produce in the atmosphere, it varies. They then oscillate some distance before they hit the Earth, so that has to be accounted for. If you had to redo the full propagation to the Earth for every different production point, that'd be very expensive. But actually, the rest of the production is the same. We keep all that information. As you change that, it doesn't need to recompute anything, which will save a lot of time. So just some results, just what do atmospheric neutrino oscillations look like. Here are what we call oscillograms. So we have neutrino energies in the ranges in question, so a couple of GeV up to 40 GeV, and then zenith angles. So -1 here is core crossing, so that's coming right up from your feet or your butts. 0 is kind of Earth skimming, coming in sideways, and the positive things are coming down from above. And you can see in the disappearance channels here, there's a big minimum there. This is like what Super K measured. This is their famous result, is measuring this big white thing there. But you can also see that depending on if it's neutrinos or antineutrinos in the normal ordering, that's the opposite of the inverted ordering, I'll show in a second, you get a huge feature in the core here, in neutrino mode, but you get nothing for antineutrinos. Atmospheric neutrinos are mostly neutrinos with a subdominant antineutrino component. The appearance probabilities also see features that are quite different between neutrinos and antineutrinos. If I flip the mass over, I'm going to go back and forth here, right? Basically, it's basically the same as flipping it left to right. The leading order, the inverted ordering, that's where lepton squared 3, 1 is negative, is the same as switching from neutrinos to antineutrinos, which is kind of cool. So if you see this feature here at a small level, that means it's in antineutrinos, which means it's the inverted ordering. You see it at a large level, that means it's in neutrinos, which means it's in the normal order. And that's something atmospheric experiments are trying to do now. There's about 2 sigma evidence that it looks like this, and not like this, but it's unclear.
What's the cause of that effect?
Yeah, so it's a resonance through the Earth's core. Good. So remember you asked earlier about that S thing, which is how the oscillations change in matter, how the frequencies change in matter. The Earth's core is the densest part of the Earth. In there, the frequencies change, and the delta M squared gets larger, which means they oscillate on shorter distances. And it's actually such that for some energies, the oscillation wavelength is comparable to the size of the core. So what you can get is as it goes through the core, the basis will go through 1/2 oscillation, and you get a maximum change, or 3/2, or whatever. And you get an enhanced effect. This is actually what comes out of that famous Mikheyev and Smirnov paper from the 80s. Yeah, but it's a sign-dependent effect. So as you can see here, if you switch the sign on the matter potential by switching to antineutrinos, there's absolutely no effect. It goes in the wrong direction. It would be impossible to see it. I mean, it is in principle there, but it would be impossible to see it. Here, it is very manifest. And it has to do with the relative sign between the matter potential and the delta m squared, which governs the frequency. So if I switch the sign on the delta m squared, then I also have to switch the sign on the matter potential, so I have to go from neutrinos to antineutrinos. Yeah. It also happens in appearance as well, but it's a little bit more complicated because appearance is harder to see. You can also use things like this to actually measure like the size of the Earth's core. I did a project with a PhD student on that. So if you can measure this very well, in principle you can see how big the Earth's core is, which is kind of cool.
But how is that normally inferred?
Seismographic data, which is presumably pretty good, but a fun fact, they don't put error bars. There's no error bars on any paper. I read many, many, many papers trying to find, everyone says the same number for the radius of the core, and I wanted to know how precise is that measure. I assumed it was much better than neutrinos. I assume it is. Neutrinos are not very good at this, unsurprisingly. What is the uncertainty on that number? There's no papers on it. I found one paper that got so close. They said, we did 50,000 simulations of different Earth models and fit them to our seismographic data sets, which obviously I cannot do that. I have no idea how to do that. We then took an error assigned by the range by the best 1,000 simulations. And I was like, you did so much work. You almost got there. And then you just made it up.
At least you have an upper bound on the size of the core.
So, do I have, there's not from the data.
We're not in the core now.
We're not in the core now. Yeah. No, you can do some elementary things. You can do better than the elementary test with neutrinos, but no, you can get about a 10% to 15% measurement of the radius of the Earth's core with neutrinos in next generation experiments, which is, I don't know, not terrible. Also, I've learned a lot of geology for that paper. I'm getting on a tangent here, I apologize, but you asked. People are learning in the last 5 to 10 years that the Earth model that I showed back here, the spherically symmetric picture, incredibly naive. The Earth's substructure, there's many more substructures. There's like continents on top of the core that have some thickness and some size. There are plumes coming up. There's all kinds of things with presumably varying density in there.
I mean, so in that case, like you could have, I mean, it could be very non-adiabatic transitions in that regard,
Yeah,
right?
so there, I mean, obviously at these boundaries there are non-adiabatic transitions that are already happening. I mean, that's why you see these sharp that sharp feature, that line. I mean, it looks like a line there, but it's not. That's just what comes out of the code. That's because there is a sharp feature in the Earth.
Right, but when you like segment the trajectory into those 4 parts, each part you were assuming constant density, right?
No. Yeah. So this is just for computational purposes. Within each one of these lines, within this blue line, let's say, I may put in 100 shells. Right? And so to model this, for example, one of these is this orange curve, which is kind of like my favorite one, which is 2 layers in here, the innermost part, each of which is constant, each of which I assume is constant. I do 10 here, 10 there, and 5 there. But I also do like a million. Okay. So where each one, it is constant on each step. I mean, this is basically solving the Schrodinger equation with like a million steps. It's the same thing. But I just instead of calling it that way, I just call it in terms of shells.
Gotcha.
The advantage of doing shells is that the density of the shell is equal, so the eigenvalues are the same no matter the trajectory. So I can actually reuse my computations for that, and it saves a bunch of time. As opposed to redoing the Schrodinger equation from scratch each time, because each time you're doing it, you're propagating, the distance might be different, but the density is the same, which means the eigenvalues and the eigenvectors are the same. So you'd be redoing the computation like way more times than you have to. But yeah, good. You can also do solar neutrinos, right? So solar neutrinos during the day, pretty easy to do. But at night, they go through the Earth and they experience a matter effect. There's actually more electron neutrinos coming at you during the nighttime than during the daytime. Sounds a little weird. But if you only saw neutrinos and you could see solar neutrinos with your eyeballs, you would think the day and night were the opposite one. I don't know if you guys noticed. This is what we expect to see here as a function of energy during the daytime in blue and during the nighttime in orange, so it's like a couple % more. This is what the probability for that actually looks like. It's like really fast oscillations. You can never see this, but you average it out and you get a couple of % enhancement. This is something that hasn't really been measured yet. We expect it to be there from what we know from other things. But next generation experiments should get 5 sigma for it. So, you got to compute this. That's a lot of probabilities to compute. Okay, so this is, now how good does this algorithm work? I'm pretty much out of time. This is the impact of the different approximations. Remember I said we approximate these eigenvalues. I showed some precision before. I'm doing it again now. It's basically the same. Without any approximation, it's 10 to the minus 5 or better. As you add in one of those Newton-Raphson iterations, it gets, it's like 5 orders of magnitude better. And for this, when I'm saying the error in the probability, what I mean is I take a grid of 100 by 100 in energy and zenith angle. I compute all the probabilities. I compare it to some very high precision calculation. And I compute the maximum and the mean error across that. And that's what's plotted. The maximum in orange and blue is the mean. Now, as you vary the Earth model, and this goes to your question, as I added more and more layers, like 10,000, 100,000 layers, what is the typical difference between that and my perfect one, which is 1,000,000 layers? You can see the error is very, very small. So in reality, for experiments, you only need like 50 to 100 layers to be far more accurate than you can measure. How fast is this? It's fast. Okay, I promise it's fast. This shows here that as you loop over the slow parameters, as the Earth model gets more complicated, of course, it takes longer to run. But for some of the fast parameters, like theta 2, 3, which remember I said factorizes out, it doesn't take any more time. You make your Earth more complicated, and the computational time to compute is basically the same. Because you only compute it once, and then you compute it 100 more times, and each successive one is basically free. We can compare this to other things in the literature. So this is the other kind of thing that's commonly used. It takes 40,000 for the same thing. For us, it takes either 6,000 or 200. So it's a lot faster. But they do other stuff. They're not bad. This is what it looks like. These are all the features in it. It's very intimidating, I think. But you can ignore most of it. To run it, you initialize your engine. You set your oscillation parameters. You load in your energies and zenith angles. You load in your Earth model. Remember I said like that 2, 10, 10, 5. You can do different things there, whatever you want. You load that into it. Then you just say compute and stuff. But you can also play around with a bunch of other stuff. And this will be online probably this week. We make recommendations for how to do it. The most important one is to put your loops intelligently. And these are my conclusions. So I've been here talking for an hour straight. Disappearance can discover CP violation, going all the way back to the beginning of my talk. It seems like it's CP conserving. You can get information there, but you have to have both JUNO and either DUNE or Hyper-K. So experiments should break down their analysis, do a full analysis, but then split it up into appearance and disappearance, because the systematics are so different for new media disappearance than they are for new media appearance. We provided, these fast codes. They've got, new linear algebra tricks, some approximations that are very good, and we really minimize the computations and save the results. And this long baseline code is already implemented for a lot of experiments, and we're hoping the atmospheric code will be too. So that's all I've got. Thank you. Any more questions?
The nighttime difference between the electron neutrinos versus the day, this is from conversion in the Earth's core, or going from the sun to the through the Earth.
Mm-hmm.
You get slightly different conversion probabilities because of matter effects.
Mm-hmm.
Is this observable in just one night, or like do you need many hours? Because could you do this to the moon during a solar eclipse?
Yeah, okay, good. I've thought of that. No.
Probably too brief.
So to be clear, Super-K has been running for 20 years. They haven't seen it yet.
Yeah.
Their evidence for this is 2 sigma.
I see.
Right, so this, to get a 2% effect, solar neutrino measurements in general are kind of bad. Right, it's the first evidence we had historically, but of course it's not the best, right? There are better ways to do this now. Seeing an additional 2% effect is not easy. And actually, because of the latitude, the effect is actually a little bit worse there than this one I'm showing here. That doesn't matter. So yeah, they haven't seen it yet. So can you see this through the moon? No one's calculated what the impact of that would be. I think that maybe my next undergraduate student, I will do that with them.
Okay.
Because I think that would be super, super fun. Is there an oscillation length that corresponds to the size of the moon? I think no, but obviously there. I've also checked the number of eclipses over the Kamiokande site when they've been running, and it's like 2.
Yeah.
And the event rate, the eclipse lasts like a minute.
Yeah.
Right? And the event rate is like like they might have seen like one neutrino at that time, but the background rates are very high. So they actually don't publish any like events for their solar neutrinos. They just, because the background rates are so high. So they look for the direction, but the directionality uncertainty is not very good. So when they publish the results, it's a huge, very complicated analysis, and you can't just like play around. This is not like long baseline neutrinos where they measure 100 neutrinos and we know every single one of them by personally. Yeah. So, but that would be fun.
Why Brookhaven doesn't have results on that?
On day-night.
Yeah, like they kind of.
Yes, they don't have as many. I think their statistics aren't as good enough. So Brookhaven, very good for low energy. Right, so their claim to fame, their main claim to fame is very low radio backgrounds, and they've measured the entire neutrino spectrum. So they've gone from PP all the way up to boron 8, picking up beryllium 7, PEP, CNO, and boron 8 along the way. They haven't gotten HEP, nobody's gotten HEP yet, but we'll get HEP soon. The boron 8 measurement, and this, the boron 8 is the highest energy part. That's what's dominating. This boron 8 and also HEP, but HEP is much harder. The boron 8 measurement is not nearly as good as superK's. For boron 8, you've got SNO, which is the original, which is pretty good, Brookhaven, which is not that great, and SuperK, which is much better. And SuperK is continuing to improve year after year. Brookhaven is done. That said, Hyper-K won't necessarily be better than SuperK, as we were talking about earlier. The backgrounds will be worse. They haven't really published a sensitivity study for it at all, because I suspect they know it's going to be worse. So what we get from SuperK over the next couple of years might be one of the most important data sets. DUNE will also do very well and possibly better, but it's a very different measurement.
Can I ask a dumb question?
Yeah,
Sorry.
no,
Thanks for the
please.
great talk. If you could put your finger on like the one thing you're most excited about in the world of neutrinos in the next few years, what would you place your money on?
That's obviously is a loaded question.
Yeah.
In the next few years, I would say, so I do get asked a lot about timescales of neutrino experiments. It's a very hot topic, and I'm being recorded. I'm not going to say anything about that because I'll get in big trouble. I've gotten in big trouble before for saying.
You can end the recording right now.
I will say things that are publicly known, which is that JUNO has started collecting data. I'm very excited about JUNO for a lot of reasons. They'll get some information on the mass ordering, 2.5 to 3 sigma over the next 6 years. Exactly what that is depends on all the usual nonsense. But before then, and I think, as I alluded to, possibly in the next few weeks, I hear they're going to post a paper about the solar parameters, what I'm calling the solar. Basically, redoing the Kamlan measurement. And I'm just going to. It's some of these too many slides.
Theta 1, 2? Or?
Yeah, theta 1, 2 and delta n squared 2, 1. I'm really excited about it. These are numbers that people don't talk about very much. So it is this. Right? It's this big dip here, right? So can you tell the difference between these wiggles? Super hard. They're not, obviously they're not there. They've been on for like 2 months. Can you tell that you are not up there and that you are down there? I'm assuming they can answer that question. Right? That's going to be the first thing, is how deep is that and where is this minimum? How deep it is theta 1, 2. Where it is delta n squared 2, 1. Delta m squared 2, 1 has really only been measured by Kamlan. You get information from solar, it's not very good, it's actually confusing and different, they're saying different things. I have no problem with Kamlan. Kamlan is probably fine, but having another measurement of it would be very nice. Same for theta 1, 2, it actually comes mostly from solar data. So basically both of the numbers they're measuring kind of only have really one input into them. So getting a cross-check and getting improved precision is very good. In addition, these parameters are key inputs for other things. In particular, CP violation. I wrote a paper with a postdoc of mine where we said, how did those parameters affect DUNE's ability to measure CP violation? If they turn out to be a little bit larger, a little bit smaller, it is easier or harder by like a sigma or more to see CP violation. So I'm going to be paying very close attention if those numbers are trending up or down or left or right. I've got other papers where I show if they're in this direction, how much easier or harder it is or whatever. So if they're meandering in that way, they may make it easier or it may make it harder for other measurements. So that's something I'm excited about in like the next month, and follow-ups to that in the next few years. It's something that I think not a lot of people are excited about, but I'm very excited about that.
Thanks, Peter.
Thank you.